We will now compare the efficiency of different fuels using different scales or different viewpoints. As was discussed on a previous slide, we can compare the heat of combustion of various substances on the molar basis using the standard combustion enthalpy expressed in kilojoules per mole of substance. On this scale, the larger the molecule, the larger the heat released per mole of molecules. However, we have already concluded that such a comparison may not be useful. We can also compare the efficiency of different fuels by comparing the heat of combustion per gram of substance. To do so, we define the specific enthalpy as the ratio of the standard combustion enthalpy to the molar mass of the fuel. On this scale, hydrogen becomes the most efficient fuel, releasing 142 kilojoules of heat per gram of hydrogen. While hydrogen fuel cells are receiving a lot of attention today, there are a number of practical issues associated with this fuel. First, hydrogen is a gas, and a gram of hydrogen occupies a considerable volume under ambient conditions. Another way to compare fuel efficiencies is to compare the heat of combustion per liter of substance. To do so, we define the enthalpy density by multiplying the specific enthalpy by the density of the substance. On this scale, gases are obviously at a very strong disadvantage, and isooctane is the most efficient fuel. So, since the efficiency of a fuel depends on the method of comparison, how can we decide which fuel is best? Actually, what we need to think about is the application of the fuel. For applications which need to deliver the largest amount of energy from the smallest mass of material, then hydrogen is the perfect fuel. For applications which need to deliver the largest amount of energy from the smallest volume of material, then isooctane is the best fuel. And that is why we are currently using fossil fuels high in isooctane to power our cars. Obviously, if we could pack hydrogen gas molecules under ambient conditions with the density characteristic of the liquid or solid state, we would have a fuel that would not only be extremely efficient for all applications, but we would also have a fuel that would not produce carbon dioxide, a greenhouse gas. Let us now compare the efficiency of the typical commercial fuels to these of the biological fuels animals and humans use for metabolic activities. We see that the enthalpy densities for glucose and tristearine are very similar to that of isooctane. Our daily energy input is somewhere between 9 and 12 megajoules, which corresponds to about 2550 to 2850 dietary calories, or kilocalories, or about 650 grams of glucose. Again, note that tristearine and lipids in general are less oxidized to start with than sugars and release more energy during absorption and digestion. Now, this is more than a motivational slide. While I'm not going to give you any dietary advice and certainly have no interest in endorsing any fast food brand, I wanted to use this slide to show that thermodynamics and the first law have direct application to the field of nutrition and exercise. As is commonly said in the field of physical fitness, what matters in calories is calories in and calories out. This slide details the food calories associated with a Big Mac and a milkshake and suggests that you could get your daily caloric input from simply 2 Big Macs and 2 milkshakes a day. It also shows the amount of time specific activities would have to be carried out to burn such calories.